So the last special transformation that we're going to be looking at is absolute value functions. New seating plan, pick wherever you'd like. And so we have what happens if you put any function inside absolute value bars. Well, if you think about what do absolute value bars do, what does an absolute value bar do to a positive number? Nothing. It keeps it exactly the same. What does an absolute value bar do to a negative number? It makes it positive. Right? Now, definition of an absolute value bar for a number is really asking you a distance. How far away is 5 from 0? 5 units away. How far away is negative 3 from 0? 3 units away. And so that's why, as an absolute value, because it's looking as a distance away from 0, it always makes a number positive. So what does that mean when we have y equals the absolute value of f of x? It means that your entire graph will be above the x-axis, because all that it's doing is it's changing all the y values to be positive. That's the only transformation that's taking place. So we're going to look at a couple of examples of this. And we'll start off with one which you could do with transformations, but the new technique that we're going to use might be better. So we want to graph the absolute value of 2x plus 3. And we're going to start with our new technique. Our new technique is graphing f of x first, which is our function inside. And then once we've graphed our inside function first, we are going to reflect all the negative y values over the x-axis. Because that's what an absolute value does, is it changes y values that are negative to positive. And if you imagine that happening, if you imagine a negative 4y value going to a positive 4y value, can you see it flipping over the x-axis? A negative 2 value would go to a positive 2. Negative 7 to a positive 7. They're all flipping the entire graph over the x-axis. So if I would graph 2x plus 3, okay, and I'm going to add to this, because they're going to be important points. When you graph your f of x function first, label your x-intercepts. So 2x plus 3, well, that has a y-intercept at 0, 3. And because it has a slope of 2, we would go up 2 over 1. Down 2 over 1. There's our line. And in addition, I want to label my x-intercept. Algebraically, how do we find an x-intercept? We set y equal to 0. And so our x-intercept would be negative 1.5, comma 0. Once you've drawn your graph, wherever your graph is negative, which is this section right here, wherever the y values are negative, that part of the graph, if you change those y values to positive, it's like flipping this negative part up over the x-axis. So this green graph is f of x, which is 2x plus 3, and underneath it here, we're going to graph the absolute value. Label your x-intercept again. This part of my original graph, where the y values were positive, are going to stay exactly the same. But this part of my graph, and I'm going to label a couple of points on it just to give a sense. For example, you would have negative 2, negative 1. You would also have negative 3, negative 3. And if my y values become positive, I would now have negative 2 comma positive 1 and negative 3 comma positive 3. And what that does is this part that's highlighted in blue just gets reflected over the x-axis. So the simplistic thing that the absolute value does is it changes all of our negative y values to positive. And it keeps all of our positive y values the same. Graphically, what that does, if you want to do it really quick, is you just have to highlight wherever your y values are negative, they get reflected over the x-axis. The old way. The old way of doing this, using Chapter 3, our very first unit, transformations, you would have your parent graph, y equals the absolute value of x. And then you would say, new seating plan, pick wherever you would like to sit. You would take your absolute value x graph there, and then you do transformations. What would the 2 do? Multiply your x values by a half. What would the 3 do? Well, be careful, because you might want to say move it 3 to the left, right? But this is one of those situations where we have a horizontal stretch plus a horizontal translation. And so before you could even do your transformations, you would have to write it in factored form. And then I would take points on my original graph like 0, 0. Maybe I would choose 2, comma 2 and negative 2, comma 2. First thing, in this first arrow, we show all of our stretches and compressions. So you would do x by 1/2. This one would stay 0, 0. This would become 1, comma 2, and negative 1, comma 2. And then you would move all of your values 3/2 to the left. And so this would become negative 3/2, comma 0. This one would become negative 0.5 comma 2, and this would become negative 2.5 comma 2. And you would go to graph it and our first point, negative 3/2 comma 0, and we would have negative 1/2 comma 2, and negative 2.5 comma 2. And with the transformations unit, because we had to factor and remember that idea, and because our translation is 1.5 to the left, we end up with a lot of fractions, as compared to this new technique, which says graph the inside function first, and then whatever's negative, flip it up over the x-axis. Our final graph here is exactly the same. But the nice thing about our final graph here is the only fraction we were dealing with is our x-intercept. And the rest of our points ended up being nice points. But this is a good review of transformations as well. So now let's combine Chapter 1. Chapter 1 had graphing polynomials. And so here, f of x, the original function, is one of the polynomial functions that we graphed in Chapter 1. So a little review of graphing in Chapter 1. This is an x cubed equation. We can tell it's an x cubed equation because it would be x times x times x. And it's already in factored form. What made Chapter 1 a little bit more challenging is sometimes you would have to factor that original equation. But this equation's already factored. And because it's an x cubed graph from Chapter 1, I mean the graph is given to you. Okay? But if you weren't given the graph, because it's an x cubed graph, you know that its end behavior acts like a line. So that's why it starts down here, ends up here. Once you've factored it, you figure out the zeros. We can see from the factors that the zeros are 0, minus 3, and plus 2. And so once you knew the end behavior and you knew the zeros, you could graph it. You wouldn't know how high it gets here or how low it gets there. That's okay. You would just draw a smooth curve through those x-intercepts with the correct end behavior. And now we want to graph the absolute value of that. So once you've graphed your initial function, all the absolute value does is change y values to positive. And so if we highlight the sections of our original graph where the y values are negative, to graph y equals the absolute value of f of x, the positive parts are going to stay the same, and the negative parts are going to get reflected over the x-axis. And so the blue graph is the graph of the absolute value of f of x. Finally, we're going to look at sometimes you can have an absolute value function with a transformation afterwards. So we're going to graph the absolute value of the square root. Which square root graph do I want to do? I'm going to do the square root of x minus 2 minus 3. So we can combine what we're learning right now about absolute value functions with some transformations. Whatever graph this absolute value is, what will the minus 3 do in the end? What does the minus 3 do at the end in a transformations graph? It moves it down 3 units. So what we're going to do is we're going to graph this absolute value function first, and whatever graph we get, after that, it's going to get moved down 3 units. So how do we graph this? Well, first we would graph the inside function. So our absolute value square root graph moved down 2 units. What does that look like? Well, we would have 0, negative 2, 1, negative 1, 4, comma 0, 9, comma 1. So I just use my transformations unit to take my square root graph and move it down 2 units. This is the graph of the square root of x minus 2. Which part of this graph is negative? If I highlight the part that's negative, that would be this section. On the same graph, I'm going to graph the absolute value of the square root of x minus 2. What's going to happen to 0, negative 2? It's going to be 0, positive 2. What would happen to 1, negative 1? It would change to 1, comma 1. And this part that's underneath will get reflected above, because that's what an absolute value does. It takes all of your negative y values and reflects them over the x-axis. And this part that was positive will stay. So it is a weird looking little graph right now, because it's got that part that reflected up. It's kind of got a little sharp point here where it was reflected at the x-intercept, and then curves up. And once we have that graph, we've got this graph. Now we can do a final translation 3 units down. So our point that is at 0, comma 2, when I shift it 3 units down, will be at 0, comma negative 1. Our point that was at 1, comma 1, when I shift it 3 units down, it will now be at 1, comma negative 2. Our x-intercept that was at 4, 0 will now be at 4, negative 3. And our point at 9, 1 will be now at 9, negative 2. And the shape stays the same. Okay, I'm going to give you one to try on your own. Check how you did. The black graph is the graph of x minus 2 squared minus 4. So that's your x squared graph. Move 2 to the right and 4 down. I labeled my x-intercepts at 0, 0 and at 4, 0. Of course, oops, plus 2. If you move 2 to the right and 4 down, then your vertex would be at 2, negative 4. In the second graph, the blue graph, that's just the absolute value of the black graph. So the negative part got flipped up over the x-axis. And so the point that was at 2, negative 4 becomes 2, positive 4. And finally, in the purple graph, everything got shifted 1 unit up. So instead of 2, 4, you have 2, 5. Instead of 0, 0, you have 0, 1. Instead of 4, 0, you have 4, 1.